Hello and welcome to section 4.6. We're going to be doing something called related rate problems. These are problems where your variables relate to time. All of them relate to time. So we'll take a derivative with dx dt, dy dt, z dz dt. Everything is related to time. All the variables change with respect to each other and time. Okay, so we also have in this a 7-step process for doing each of the problems. We're actually going to use this time. I think in section 4 we didn't necessarily use it, but we are going to use this time, and so we will go by each step. There are 4 famous problems on this. There's the balloon problem, the police chase, or the highway chase, whatever you want to call it, the filling of the conical tank, and also the flying kite. So this first one is the rising balloon problem. A balloon is raised straight up from a level field. It's tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's elevation is pi over 4, the angle is increasing at the rate of 0.14 radians per minute. So how fast is the balloon rising? Okay, so the big thing about these problems is setting up a picture and figuring out what you're looking for, what numbers are fixed, and what numbers change with time. Okay, so that is our big process. So the first part is to draw the picture. Right here is the liftoff point, and over here, 500 feet away, is the rangefinder that they call. That x value is a constant. And our first step says to draw a picture, figure out what are constants, what are variables. Okay, x is 500 feet. That is not going to change. Variables, we have theta, because that's a variable, but at one point in time, they give us that that theta is pi over 4. Okay, so theta is a variable, but they give us one point in time, and they also say that it is increasing. So that means that our rate of change for theta with respect to time equals 0.14. And remember, in calculus we always use radians. So when this is pi over 4, d theta dt is 0.4. That's at one instant in time. And actually that's part number 2, where we write down the additional numerical information. Another variable is y, because the balloon is lifting off, or lifting up. Okay, the second part says write down additional information, and we write down at theta equals pi over 4. We know that the change in theta over the change in time equals 0.14 radians per minute, I believe it is. Okay, so what we want to find is how fast the balloon is rising. That is going to be dy dt. So that's number 3. What are we looking for? Number 3 is an important question. What are we looking for? We're looking for the change in time at theta equals pi over 4. Okay, so when that happens, when theta gets to that rate, that's what we want to know. All right, so the equation we can use to relate an angle, an opposite side, and an adjacent side is, oh my, good old tangent. Okay, so tangent of theta equals y, opposite over adjacent. Now, adjacent is 500 and it's fixed, so we don't really need to use a variable for it. And you'll notice that in these problems, on the horizontal axis, I usually use an x. On the vertical axis, I usually use a y, just to be consistent with our coordinate plane. Okay, so another way to write this might be y equals, multiply both sides by 500. Okay, so step 5 says differentiate with respect to t. All right, so if we take the derivative with respect to t, 500 is a constant. The derivative of tangent is secant squared times d theta dt equals dy dt. Okay, we differentiate both sides of this equation. All right, and now we're gonna plug in the numbers we know, which we know all of them except what we're looking for, and then we'll get an answer. Okay, so this is number 6 where we evaluate the rate with the given values. All right, so 500 secant squared pi over 4 times 0.14 equals what we want to know, okay? Put this into your calculator. Secant is 1 over cosine. So put that in your calculator and you should get 140 feet per minute. And that is how fast the balloon is rising at that time. And then if we look at, the next thing says to evaluate, interpret the results. Okay, and that's kind of what I just said. The balloon is rising at the rate of when the angle is pi over 4. Okay, good problem. Next problem is the famous highway chase. Okay, so this is the famous highway chase. We have a police car coming here, going south. It's coming from the north. This second car has just turned right at the corner, and it's moving east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles east, the police determine with radar that the distance between them is increasing at 20 miles per hour. All right, so we have a little triangle here, and we want to know the speed of this car. So we want to know dx dt. All right, we want to know that speed. All right, so number 1, x, y, and z are all variables, or x, y, and s. Second of all, other information we know is that when y equals 0.6, x equals 0.8, and at that same moment, ds dt equals 20. All right, so let's see, and we know that this dy dt is 60 miles an hour. We have lots of numbers here, okay, but they're all in one instant. Number 3, we determined that we want to find dx dt. This is good. Number 4 says that we want to write a relationship between all of these variables. Well, I'd call on Pythagoras to give us x squared plus y squared equals s squared, right? That's about the only relationship we know between those triangular values. Luckily, he turned a right angle when he got to that corner. All right, now we can take the derivative. This is an interesting part. This is in your book in section 6.6, by the way, too. It's taking derivatives with different variables with respect to time. Okay, so 2x dx dt. Okay, this is just like implicit differentiation, except now you're relating each variable to t. Okay, that is our derivative. Now, if I look back at all the things I know and what I'm looking for this. I know what x is, I know what y is, I know what dy is, I know what ds is. I don't know what s is at this moment. But I think I can figure out what s is at this moment because I have this equation, right? So if we take 0.6 squared plus 0.8 squared equals s squared, I think we can get a number for s at that particular moment. And s is actually equal to 1. So now I have all the numbers I need. So part 6 says evaluate. Oh, this is so exciting. Okay, so let's evaluate, see if we can keep all of our numbers straight. 2 times 0.6 times oh, that's not 0.6. That's actually 0.8, isn't it? Okay, so 2 times 0.8 times dx dt, which is what we're looking for, plus 2 times 0.6 times, what did they say this is? 60 miles per hour equals 2 times 1 times ds dt, I think was 20. All right, so we're going to get an answer here in miles per something. So here we have 1.6 dx dt. Let's do a little fancy math. 2 times 0.6 times 60 minus 72 equals 40. Okay, so if we solve this equation, we should get dx dt, I think I did my math right. Dx dt equals 70. I believe that's what we should get, mph. And so 7, we evaluate the car's running away speed is 70 miles per hour. That's evaluating, just recapping what you got. Make sure 70 miles an hour makes sense. Okay, the next problem is the conical tank. This is the one where people have the most fun. So we have water running into this tank at a rate, and that's a volume rate. The tank stands point down, which I don't understand. How does it stand up? But whatever. And has a height of 10 feet and a base of, and a radius of 5 feet for the base, which is not really the base because it's on top. But anyway, how fast is the water level rising when the water is 6 feet deep? So we have a water level here indicated by X and Y, and it rises. Our volume is also a variable. Things we know at a certain, things we have as constants. We know the radius is 5, we know the height is 10. That does not change. We also know that at a particular time, the change in volume with respect to time is 9 feet cubed per minute. All right, and we also want to know how fast is the water level rising when the water is 6 feet deep. So we want to know when y equals 6. That's 6 feet high, yes. Okay, so number 3 says, what are we looking for? How fast is the water level rising? So we're actually looking for the change in y over the change in time. How fast is it rising? Okay, what equation can we relate these things to? Well, going back to, I don't know what subject, geometry, we know that a cone volume is 1/3 pi r squared h. All right, cool. Well, we also know that we have h and r relating to x and y. So we're going to do a little fancy magic with that as well. We have, we can set up a ratio with r to h is equal to x to y. Right? The radius over the height. And also r over h is constant, so we know that equals 5 over 10. So if we write our x and y's as r's and h's, because that's what our x and y's really are. We have v equals 1/3 pi x squared y, because really that's what we're going to be measuring, the x and y, not really the r and h that are fixed. All right, so we can take this equation and let's solve for y and make it into a y equals equation. So let's cross multiply 5y, we could have reduced that, but 5y equals 10x. Divide both sides by 5. We get y is equal to 2 x's. All right, so that's what we're going to plug into the equation, except let me step back and reevaluate a moment. We are going to be looking for dy dt, So when we take this derivative, we are going to want to have only y's in our volume equation. So I want to retrace my steps and actually solve for x. So if y equals 2x, that means x equals y over 2. That is what I'm going to want to substitute in here. And then when I take the derivative, I have the dy dt that I'm looking for. So let's put in volume equals 1/3 pi. We have y over 2 instead of x squared times y. All right, let's do a little bit of fancy algebra. Okay, 1/3 times 1/4. Remember, this is y squared over 4 here. So we're going to multiply 3 times 4. We'll get 1/12. We'll get a pi. And we'll get y squared times a y to the 3rd power. Phew, okay, we made it through that. That's the equation we are going to take the derivative of. dv dt equals pi over 12 is just a constant, so just let it sit there. And then we have 3y squared dy dt. Okay, now we have a volume for dv. Y, oh, we have a value for y, 6. All right, so we have 9 equals pi, 12, 3, 6 squared, dy dt. All right, if you calculate that all up and do your fancy algebra on that whole little equation, what you should get is 0.32 feet per minute. That is how fast the water level is rising. Oops, wait. I took the derivative and I did number 6 here where I evaluated it right away. So I did number 6. And number 7 is evaluate your results. The water in the tank water, is rising at a rate of 0.32 feet per minute. Okay, and that makes sense, about 4 inches per minute. I mean, it's a pretty big tank, so that makes sense to me. I'll buy that. Okay, last problem is the famous girl flying her kite. Okay, so here we have a girl flying her kite. The kite is at a constant, y equals 300 feet. We told us that was constant. The x and the s can change because the kite's moving out and the distance on her string gets longer. What they told us though is at the instant where s equals 500, and we also calculated that when s is 500, x would be 400. We use Pythagorean's theorem, 300 plus x squared or 300 squared plus x squared equals 500 squared. So we figured that out. The wind carries the kite away from her at a rate of 25 feet per second. So the change in dx dt is going to equal 25 feet per second. So we want to know how fast she must let out her kite string, and so that is what is ds dt. Okay, so from our little triangle, you can probably guess that we are going to use the x squared plus y squared equals s squared equation again. Good old Pythagoras. Okay, so if we take the derivative of that, we've already done that before, so 2x squared dx dt. And most of your problems follow one of these formats. So, oops, I still need a 2s here. Okay, so I think when s is 500, we know this, and this. We have dx dt is 25 feet per second. Okay, the one thing that we weren't given was what is dy dt. Huh, well, the funny thing is that dy dt is 0 because y is a constant. And you could have actually put in 300 right here when you took your, before you took your derivative, and then when you took your derivative, you'd get a constant, a 0 when you took the derivative. All right, so x is equal to 400, so 2 times 400, and dx dt is 25, and plus 0, and that equals 2 times 500. ds dt is what we want to know. Okay, so we have 1,000 ds dt's equals 20,000. Divide both sides by 1,000, and you get 20. So ds dt, that means that the distance, let's see, that the kite, how fast she lets out the string at, kite string must be let out at a rate of 20 feet per second when the kite is 500 feet away. From her. Okay, and that's the end of our famous related rates problem. All 4 of them are famous, been around for hundreds and thousands of years.